This worked. It detected hits reliably and it lit up on impact. I'm creating a modular smart target system for Airsoft and Paintball. I'm Ben, and let's get started. So this was the first version. It was quite literally the MVP. I took off-the-shelf components, put them together, and tested to see that the system would work. What I'm going to do now is I'm going to start developing that into a full product. There's engineering that's going to be required, business side that's going to be required, and ultimately launching the product on Kickstarter. I'm going to change some of the components out as we go, partially for cost basis and partially for functionality, but ultimately the system remains the same. A modular, smart target system that can give more reactive gameplay. So a bit of a recap on the first version. I designed it so that it would have a hub. It would have all of the processing done in that hub and then the targets would spoke off from that. This gave it maximum functionality in a sense of I can add different targets to one hub and have different game modes. As you can see here, single player mode, you hit all the targets and then you've done and you get the results back of how quick you hit all the targets. On multiplayer mode, you have different colours light up and then each player gets a different colour and then you hit them all and again it lights up. A lot more game modes can be created as well, such as Connect 4 and Knots and Crosses, but the first version needed to show that it was possible. One of the things I learned from the first version as well was that the mechanical setup of the system just wasn't right. I wanted to have a multi-part target, so the outside 4 quadrants would be separate and the centre would be able to be hit as well. It gives the target a bit more functionality in one target if you just wanted to use one versus having multiple separate ones, but it was just going to be way too thick, so I want to get that reduced down as well. Now if we look at the V1 design brief, there's a few key things that are needed. I need the main housing of the hub to be sealed to an IP65 plus rating. That's so that it can be used outside without any worries of water ingress. The sensor pucks which are going to go on the back of the targets will need to be the same, so they can be hot swapped as well, but without there being any issues of water getting in. There needs to be a power system that's going to withhold 12 plus hours of runtime, and that's so that you can get full day's use out of it, as well as also being able to be plugged in and used while being powered. That way they can be plugged in indoors and just left permanently on. As well as this, because I'm aiming to do it as a Kickstarter project, I need to make sure that the bill of materials cost is as low as possible, whilst using production ready components. That way I can make sure that the margins are high enough that on the Kickstarter I'm able to give away good deals, and also after the product is then released, it's still competitive in the market. Now before I go any further, I do want to try and structure the series a bit. There is a lot of engineering that's going to be required, as well as the business side of things to make sure that the Kickstarter is successful. There's a lot to do when coming to setting up a business and to creating a product, and I want to make sure I split them and give equal amounts of time and information on both the engineering side and the business side. Some of the topics you can see here, and they are very broad and there's a lot that's not covered here, but I'm going to try and do the best I can. So let's start with the V1 block diagrams. I'm going to break it down to two parts. We've got a main housing and then we've got a sensor housing. The main housing is going to be the board that controls everything. It's going to control and compute all of the game modes, and it's going to connect to the Wi-Fi, take in the power from the charger or from the batteries and charge everything else and power everything else. It's going to be rugged and sealed, IP65 at least like we've said, and it needs to be scalable and updatable in the future as different features are added. It needs to be serviceable and testable for manufacture, as well as being cost effective, not just in the PCB design and components used, but the housing and everything else that's going to go with creating that main housing of the target. The sensor housings are going to be small pucks that are used to connect to the main hub, and they're going to be targets as well, but what that does is that gives us a smaller PCB that's going to be needed and a different housing that's going to be required. It's going to have to be able to be rugged and waterproof as well, but it's going to have to be also consistent, replaceable. You can swap it out with different targets. It's going to have to be able to be low powered as well and cost effective, because we don't want to be draining the system of all the battery to get that 12-hour runtime. Now from there we can break that down a little bit further, so we can have a look at what we're going to need in each of these housings. I'm going to need a battery and I'm going to need a USB-C charger to start with. They're going to have to go through the power management system to make sure that we've got all of the power required for the different components. I'm going to use a microcontroller to do all of the Wi-Fi controls, all of the I/O, and it's going to be a low powered system to make sure that we do get that 12-hour runtime. We're going to then need a connector as well that goes between the two housings. It's going to have to be able to withstand the outdoor use, and it's going to have to be cost effective. The power regulation side on the sensor housing is going to be required as well, because we're going to need to make sure that we send over 5 volts from the main housing and then can regulate that down to 3.3 volts for the sensors. The LEDs generally require 5 volts to make sure that they get maximum brightness and control. Now that we've got all of the requirements set out, I can then determine which components are going to be required. So when I've looked at it for the battery pack, we're going to probably need a 1 cell but 2 battery 18650 pack, if not 21700. And that's to make sure that we get enough milliamp hours in the batteries or in the pack in itself entirely to handle the 12 hours. The USB-C cable side's required. It's an industry standard now, and that should be an off-the-shelf product as a little connector. The battery charge management is going to need to make sure that it has an integrated power path, and that means that we can then charge off of USB-C whilst also running the system. Following this, we need a 5 volt boost converter, and that's so that we can take the battery input and create 5 volts so that we've got full system power at all times. We then need to regulate down to 3.3 volts as well, so that we have the power required for the sensors and for the microcontroller. The microcontroller I've chosen is ESP32C3 Mini 1U, and that's because it has an external antenna option. So I can make sure that even though the case is going to be IP65 plus rated, it'll be sealed, I can still get a good signal out. That's going to help with long-term range when the product's outdoors. As well as that, it's a off-the-shelf product at a low cost, and it has enough GPIO for what we require. The 5-pin e-bike M8 connector is one of the few connectors that I was able to find online, which was cheap enough and also rated for the use that we're going to give it. I would like to swap that out for a higher pin count in future, however, but it does give us the minimum amount that we require for the test on version 1. Following the connector in the sensor side, however, we're going to have to then regulate 5 volts that we send over the connector back down to 3.3 volts for the sensor. We also need to keep that 5 volts there though, so that we can power the LEDs. As the RGB addressable LEDs, they can work off of 3.3 volts sometimes, but they do prefer to work off of 5, and 5 volts will give us the maximum brightness. I had originally chose to use an accelerometer for the project, and it would have been cheaper. However, I found the ST's LIS3 DHTR while I was doing the PCB layout, and it gives a lot more functionality with the 3 gyroscopes as well as the 3 accelerometers in it, so I can pick up the rotation of the device, not just the acceleration as the targets hit. Now this brings us onto the launch milestone, the deadlines. I'm going to set a quite aggressive target. I want to have this launched by the 31st of March. And what that means is that I've got to get a lot of development done, get the iterations of the PCBs underway, and hopefully get a few videos released along the way as well, so that it's not a case that I just document everything and then release it at the end. I want to make sure that I can bring people along for the journey and learn as well as being able to hopefully help others learn. For anyone interested in becoming a tester of the product, or if you want to become a distributor, have a look in the description and I'll put a link there to be able to contact me. As well as that, if you want a chance at winning them, like, subscribe and comment underneath the kind of equipment that you'd like to see on the field. I'm going to build these targets and then I'm going to look at other equipment that I can design and build as well. Now this is where the video originally ended, so it was a bit longer, it had more slides, but I've cut it right back because I've started to do more development of the PCB as well. So let's dive into that straight away. I can break down the main board schematic and the sensor board schematic, and we'll start with the power management. I've got a USB-C connector and USB D- and D+ broken out, the 5.1k resistors on CC1 and CC2, and that's for the USB-C orientation. It's not relevant right now, but it'll be handy for later. I've got a TVS diode as well that's on there for ESD protection, and 22 ohm resistors on the D- and D+. If we then move over to the battery power management, we've got the TI chip, and that's the power management IC. It's going to be handling the maximum current draw and the charge current cutout, and that's all done through these resistors here. I've got the schematics for these from the data sheets, and I've also calculated what resistors are going to be required based on the battery requirements. So for a single battery, the cut-off charge current is going to have to be 50 milliamps, and it will need a 1.2k resistor. We'll have to double that for 2 batteries or triple it for 3. Now these calculations are all based on the LG M52 VT battery, and I've chosen that one currently for the price and stock availability. It will also have to change if the battery does change, but we have the pads there so we can swap the resistors over if necessary. Now if we go back to the schematic, I've also added in an optional extra NTC feedback circuit. The NTCs aren't normally on these batteries, however I'm trying to get that custom added for extra security for the battery safety. The NTC feedback circuit will allow us to adjust that so that we can set the temperature range that the battery will and won't charge at. Moving on to the 5V buck boost converter. We've got the boost converter set up there with its decoupling capacitors and the resistors for the feedback circuit. And then we've got the 3.3V regulator that will take the 5V in, and again feedback circuit with the required resistors to get 3.3V out. And as well as that, I've got an optional mode change for PWM or PFM mode, and that gives us our permanent power or our low power modes. And that's it for the power management page. Thank you for watching, please subscribe. If we go over to the MCU and peripherals, we've got the inertial measurement sensor, and that's connected by I2C. I've decided to stick one of these onto the main housing as well because that can also be used as a target. We've then got the ESP32, and at the top I've got the decoupling capacitors as per the datasheet. I'll probably add a few more in there. And we've got the connected pins. Every pin that I needed to use was broken out, and I don't think there's any spare left on this module, and we'll see later how I've had to expand that as well. The charge and battery good sensors off of the charge management IC, I2C pull-ups. We've got the strapping pins as well for the eye weight, and the enable pin there, which needs to be pulled up to 3.3V as well as being able to be switched for reset. We then move over to the level shifter circuit. So I've added this in for the RGB LEDs, which require the 5V digital signal. Now if we move over to the peripherals continued, we can see that I've got I2C multiplexers, and that's to break out the I2C signals for the multiple boards because the sensors only have 2 address pins and we need multiple targets. I've got 2 sets of 8 channels, so I can do up to 16 extra targets, and they're all on the 2 I2C pins from the ESP32. I've got GPI multiplexers doing the same thing, and that's because there's not enough I/O to be able to control all the digital LED signals otherwise. I've added in a buzzer, and that gives us audio feedback to the players, as well as the LEDs that are going to be needed on this target. And that has LED in from the ESP32, and then as you can see on the level shifter, it comes out of there at 5V. If we go back to the peripherals, we can see that we've also got an external LED on the back of these LEDs, and that will allow us to do external lights. Moving on to the connectors, I've got the sensor board headers, and I've used 8-pin connectors and broken out the I2C for each as well as the digital signal, and that's on both sets of the I2C expander multiplexers. I've got general connectors there for the boot pin, which is IO9, the UART, which is the RX and TX pins on the ESP32, external LED, the USB-C bulkhead, battery and alternative power in. So we can also do the USB-C pins here like we do from the USB-C connector, and that's just going to take in the D-, D+, exactly the same, so we have the same protection from ESD. Now if we move over to the sensor board schematic, we've got the main board connector, and that's also an 8-pin XH connector like we have on the main housing. The difference is that we've only got the 5 pins connected on the main housing currently, but we have 7 of the 8 pins connected on the sensor board. And that's because I've broken the 2 interrupt pins out from the sensor so that we can take them signals in later without having to redo this board. It is at this point, however, that I realised that I've got 2 of the pins swapped. So when I went back before to do the schematic, I had to swap the SCL and the SDA pins on some of the headers to make the routing easier, but I didn't do it on all of them. So it's a good job that I went back at this point and I double checked, and I can get it changed before we do the board revision. If we now head back over to the sensor board, we can see that we've got the inertial measurement module. That's going to be taken in the SCL and SDA pins that have come from the multiplexer. We've got 3.3V power in it, and that's coming from the regulator. So 5V comes in through the connector, and then we regulate that down to 3.3V, and it's got a couple of decoupling capacitors there as well. There's a level shifter, the same as on the main board, so we take the digital signal in from the GPIO multiplexer at 3.3V and shift that up to 5 for the LED's digital input. That's then passed from one LED to the next, and then at the very end we have an external LED connector as well. That external LED connector is going to be used for any external LEDs that are going to be required for different types of the target. So that then takes us onto the PCB design. I've used a 4-layer board and I've got the signals on the top and bottom layer, a ground plane and a power plane. I've broken the power plane up into the different sections. So on the inputs we've got the voltage in, we've then got the VCC after the power distribution, 5 volts and 3.3 volts. That helps us keep the signals clean and also make sure that we're distributing the power and can use vias to be able to connect them rather than having a lot more traces everywhere. As well as having the signal planes on the top and bottom. If there is any erroneous connections, I can then sort them during the prototyping. Now, the pink outline that you see there is the board edge. The board isn't designed currently for the size of board that's going to be required, and that's because the housings had to change, but I'll get onto that in a second. On the sensor board as well, the PCB was designed. It's a lot easier because there's a lot less to control on this board. We've got the regulation on the right hand side there from 5 volts down to 3.3 and the level shifter, and then we've got the sensor in the middle of the board. Both boards have the LEDs on the other side of the board, and I've tried to keep it just to them components, because if I can get one side of the board populated with everything on, I can then manually put these on once they arrive. Now this is the enclosure that was originally picked. It's the Takachi WP series enclosure. It's the WP5 and the WP11 that I was originally going to use. However, once I've started looking at component availability, the price and the spacing as well, it's not been the viable enclosure that I thought it originally was. So that then is going to require a redesign of the PCB layout. Alternatively, I've managed to find these Hammond housings. So they're both in the same family of housing, and when I've put them into the 3D CAD model, we can see the difference that they make. This is what the original render looked like with the Takachi housings on, and this is what it looked like with the Hammond housings on. It makes more difference when you can see what it means to the components inside though. When I started to then place the components inside of the enclosure, like the PCB and the batteries there, you can see that there's not enough space to be able to put the 2 batteries in that are going to be required to try and reach that 12-hour runtime. We might also need 3 batteries, and that would just then be impossible. We're already touching the connectors and we're directly above the components. There's not enough space to safely put them all in that enclosure. Now, however, if we look at the Hammond enclosure, there's more than enough space there to be able to fit the PCB in and the 3 batteries. It's got the waterproof functionality which we require, and it also comes with a flanged base. So that base means that we can actually connect it directly to the target and the other elements that are going to be required. As well as this, there is a space for an overlay graphic to go, so we can actually put some extra lights and feedback for the users, and that makes it an even better enclosure for this product in my opinion. Now that's the end of this video. I'm going to get the boards ordered as soon as possible. There is a couple updates that I can make to the schematics before then though, and I do need to redo the PCB design to meet the new housings. As well as that, I've ordered the housings, I've started to order the connectors, and the next step really is to look at the front of the target, how it's going to look and what materials it's going to be made out of. But that's going to be something for the next video. If there's any suggestions you have for the target, please feel free to subscribe and comment them below. I'll get back to you as soon as possible. As well as all of this, there is the business side that I need to get sorted, so I've started to work on the branding. But let's finish this video with a quick animation of what I expect the target system should look like. The red is when it's ready to be hit, the green or colours are when they've been hit. The idea is obviously, as I've said earlier, a modular system, multiple targets and multiplayer gameplay, things like noughts and crosses. Thank you, and I'll see you in the next one.